So that brings us on to section 3.7 on dual spaces. So we're going to be looking at especially continuous linear functionals and the topological dual space, which we'll often just call the dual space. And we're going to want to identify it. Now, the dual space is very important in functional analysis for a lot of reasons. One way is it actually sometimes helps you to decide whether two spaces are different or not. So if you've got a subspace of a space and you want to know whether you've got the whole thing there, then often what you do is you look for linear subspace. You try to decide whether or not there's a linear functional that kills the whole subspace or not, which is constantly zero on the subspace. This is, for anybody who's learning about Swiss cheeses, is particularly relevant because when you study Swiss cheeses, you end up looking at a particular subalgebra and a very nice continuous linear functional which annihilates it. And that's one of the applications of linear functionals in the theory of Banach algebras. Right. Now, so we're going to look at quite a few particular norm spaces and identify the linear functionals on them. We'll talk about the dual or dual space, and I'm always going to mean topological dual space unless otherwise specified. And I remember that E star is our notation for it. It's the continuous linear functionals. That's, in other words, the bounded linear operators from your norm space into the scalars. But I'll remind you what the operator norm is for phi in E star. Because we use modulus on the scalars, the operator norm of phi is the supremum of modulus of phi of x, where x is in the unit ball of E, closed unit ball we can use. So you look at all x in the closed unit ball of E. You can use the open ball, you get the same thing. You can use the open sphere and you get the same thing. You can use those things whose norm is exactly 1, or you can use those things whose norm is strictly less than 1, or you can use those things whose norm is less than or equal to 1. By the time you take your supremum, you get exactly the same thing. With a possible exception of when E is a zero space and when the unit sphere is empty, and then you have to figure out what the supremum of the empty set is. So let's not worry about that special case. Now, what's really good about this is that even if E is not complete, E star is. Now, that's a special case of the following result, which says that whenever you put the operator norm on the bounded operators from E into a Banach space, even if E is incomplete, it's where you're going to that matters. So if the second space is complete, then the bounded operators from E into F with operator norm is a Banach space. And then E star is a special case where you're mapping into the one-dimensional of obviously complete one-dimensional norm space F itself. So let me sketch a proof of that, but not do it in full. Okay, so I want to sketch the proof of theorem 3.23, which I'll put here. So E is a norm space, F is a Banach space, and you'll be looking at the bounded operators from E into F with operator norm. So let's suppose you had a Cauchy sequence in there, which will be there for a sequence of operators. Let Tn, n running from 1 to infinity, be a Cauchy sequence, so an operator norm Cauchy sequence in B of EF. we've got to prove that Tn converges in operator norm to some bounded operator. Well, I'll just sketch it, but it's got a very, very familiar structure. First, you prove it converges pointwise. So you let x be in E and look at Tn of x as n runs from 1 to infinity in F. Then you can show that this is a Cauchy sequence in F. So you can use the fact that Tn is Cauchy as operators to see that Tn of x as n goes from 1 to infinity is Cauchy in F, and F, fortunately, is complete. E wasn't, maybe, but F is. And so, convergent in F. So we can now define a function, but we don't know what sort of function it is. A function, t, from E goes to F, by t of x is the limit as n tends to infinity of Tn of x. Well, so far we know very little about t. The rest of the proof consists of showing, first of all, that t is linear, which is easy. Next, that t is bounded, and that the Tn minus t tends to 0, and that's the Cauchiness stuff happening again. So finally, you show t is linear. That's easy. And that t is in B of EF, and norm Tn minus t op tends to 0 as n tends to infinity. And that's the usual, use the Cauchy condition again, as usual, in all the proofs we've seen so far. As in our typical completeness proof, let me say. We've done that about 3 times so far. This is number 4. I'm not going to go through all the details this time, so I'll leave it as an exercise to check the details. Any questions about what the result means, or about what's going on in this sketch? Any surprises here? This is an absolutely typical proof of completeness, and you just follow essentially exactly the same procedure as we've done in all the other cases. So it's the space you're mapping into that matters, and not the space you're mapping from. You end up with a Banach space this way. And in particular, when the norm space F is the Banach space that's one-dimensional, consisting of just the complex numbers or the real numbers, depending on whether you're real or complex, then you're looking at the dual space, the space of continuous linear functionals, and that's always a Banach space. So that's very nice. You start with a norm space, but you take the dual, and it becomes a Banach space. And that can be very helpful. One of the things you do, by the way, is take the double dual. You take the dual and then take the dual again, and you're still a Banach space, because you only have to take dual once to become a Banach space. Taking the dual again is overkill. But we're going to see that every norm space embeds isometrically into its double dual, or bidual, as they also call it. Okay, so this is what I was just saying. The topological dual is always a Banach space. Now, there is a problem that you're not sure whether there are any continuous linear functionals on an arbitrary norm space, and you need something like the Hamel-Banach theorem, which we'll come back to later, in order to show there are any. But take it on trust for the moment, again, depending on the axiom of choice, that there are plenty of linear functionals around, plenty of continuous ones around. So that's okay. If you're dealing with a separable norm space, which quite a lot of our spaces are, then you don't need the axiom of choice to prove the Hamel-Banach theorem. So that's slightly handy. If you don't like the axiom of choice and you still want the Hamel-Banach theorem, you get it anyway for separable norm spaces. So that's okay. So let's relate what we were talking about before about codimension 1 to linear functionals. And again, this all connects up with the isomorphism theorem, because a linear functional is a map from your space to a one-dimensional space. What are the possible images in general of a linear functional? Linear functional takes the image of a linear functional is a subspace of the codomain. The codomain is the scalars. So what are the possibilities for the image of a linear functional? How many subspaces can a one-dimensional space have? Two, that's right. Yes. A one-dimensional vector space only has two subspaces. The zero subspace and the whole thing. So when you look at a linear functional, there's only two possibilities. Either the image is the whole thing, or the image is zero, which only happens when you're dealing with the constantly zero linear functional, which is rather boring. But that is one of the options. So there's the zero linear functional, and then there are the non-zero linear functionals, the ones where there's at least one point which you don't get the value zero. And that's what I'm going to look at here. So suppose you've got a non-zero linear functional, then the image has to be the whole of the scalars. But the isomorphism theorem tells you that the image is isomorphic to the quotient of the original space by the kernel. So the quotient of the original space by the kernel is going to have dimension 1. So the kernel must have codimension 1 here. And that does the first part of this exercise. Now, that's true in any vector space. Now we suppose it's a normed space. You look at the kernel. The kernel is either closed or it isn't. If the kernel isn't closed, you can close it. But the closure of a subspace is still a subspace. So if you have a subspace of codimension 1, what do you think happens and it isn't closed? What happens when you close it? You have to get a slightly bigger subspace. But if your original subspace is codimension 1, there isn't room for anything bigger except for the whole space. So that's the next bit. If the kernel is not closed, then it must be dense, because its closure will be a bigger subspace, but it already had codimension 1, so there isn't room. You have to check a few little details to make sure that you understand, again, about subspaces of codimension 1 and why there's no room for anything bigger. But we already looked at that. Take any element outside your codimension 1 space, then it already generates a whole space using that one element.
So
That's true, but they're probably both infinite dimensional most of the time. So that's usually not an interesting calculation. In finite dimensional spaces, though, that's exactly right. And people do look at finite dimensional norm spaces quite a lot, and even though all the norms on them are equivalent, people still care, because people care about the shape of the unit ball, and people want to know how like each other two different norm spaces are. So even though they're isomorphic as norm spaces, when you take two spaces of the same dimension, they're not isometrically isomorphic usually, and you want to know how far apart are they in some sense, something called Banach-Mazur distance people are interested in. And people are interested in finding large copies of things that are almost Hilbert space inside your vector spaces and things like that. So there's a whole theory of finite dimensional Banach spaces, which I don't really know very much about. But people do care about finite dimensional ones, and in there, then what you said is exactly right. The dimension of the kernel of your linear functional is going to be, it's codimension 1 means your dimension's going to be, you've lost one dimension. You're one dimension smaller than the original space. Now here's an interesting one. Leave this to you as an exercise. This bit's not quite so easy, but it's on a question sheet. Some bits of this are easy. Suppose a linear functional is continuous. I claim then the kernel must be closed. Why is that immediate? So why must the kernel of a continuous linear map be closed? Lots of different reasons, of course. I'll give you one reason. Note that the kernel of lambda is the preimage of something. What's it the preimage of? The zero space, right? So suppose lambda is continuous. How do you know that that's closed? Preimage of a closed set must be closed. This has only got one point in it. Okay, so this is obviously, that's a single point set, so it's closed in the scalars. This works more generally, of course. The kernel of a continuous linear map between norm spaces is, again, the preimage of 0. So it's 0. So it's closed. So if lambda is continuous, then the kernel is closed. So if the kernel isn't closed, then it's dense, because it's linear functional. And then lambda is discontinuous. But the one way around that's less obvious is that if the kernel is closed, that lambda must be continuous. And that needs a little bit of work. So I'll leave that part of it to you as an exercise. And again, on a question sheet, if you've got a subspace of codimension 1, then it is the kernel of a linear functional. And in fact, there's not much choice. If you've got two different linear functionals with the same kernel, one of them has to be a constant multiple of the other. So you don't have much choice. So you've got a pretty nice correspondence between codimension 1 subspaces and linear functionals. Except that if you take a non-zero multiple of a linear functional, it's still got the same kernel. But apart from that, it's an exact correspondence. You can tell what your linear functional is up to a scalar multiple by figuring out what its kernel is. And obviously, if you know the linear functional, then you know what its kernel is. So that's a very nice connection between linear maps, linear functionals and their kernels, which, if you have a good look at that, it'll give you a decent understanding of what sort of thing a linear functional can be. And again, if you're looking at finite dimensional spaces, you're then looking at the subspaces which are one dimension down. And if you're looking in three-dimensional space, then you'd be looking at two-dimensional subspaces, which would be, so if you're looking at R cubed, then the kernels of interesting linear functionals are going to be planes through the origin, and the linear functionals are going to be something like dot product with a normal, that sort of thing. And then finally, slightly trickier stuff, using Hamel Basis. Every infinite dimensional norm space has a discontinuous linear functional. Without the axiom of choice, you're not going to find anything, because you're never going to find an explicitly defined discontinuous linear map from a norm space into a Banach space. I can pretty much promise you that. But the fact that loads of these things exist, using the axiom of choice, is another matter. But what you can do, although you're never going to find an explicit discontinuous linear functional defined on a Banach space, you can find explicit discontinuous linear functionals defined on norm spaces without using Hamel bases, and you can do that using our favourite C00 space. So, hint, use C00 as usual with some norm. You can choose which of your favourite norms to put on it. I haven't done any of these examples for you at all yet. So I guess they are all turning up on question sheets. I think we should stop there, but have a think and let me know if you're having trouble getting any of these examples using C00 to work. I can always run through one of them in a lecture so that you can see how you do something with C00 to get you interesting examples of badly behaved operators. Okay, we better stop there today.